Oh, I don't have a physics class for a while now, Bob.
Yes!
There's not enough alcohol in the state of Wisconsin for me to survive that. All right. Now,
You just said the F word, young lady. She did not say quiet.
all right. So, let's do this problem. We're going to rock on with these right here. Last time we met and we did some calculations. Again, impulse, force times time is equal to the change in momentum. So this really is contact time, follow through, things like that. Change in momentum. Momentum is just mass times velocity, but your mass doesn't change, your velocity changes. So there's our impulse momentum theorem. Okay, so this problem here describes, this is the contact force for a baseball. This would be the maximum compression of the ball as it's on the bat, would be when the ball is the flattest at the top probably, and then this kind of springs back, right? The ball starts to flatten here, it's done flattening here, and this would be the max. And it says this has an effective force across here at this line at 480 newtons. So I'm just going to write down what I read here. We have a force, or we got a mass. We've got a mass of 150 grams. How many kilograms? 0.150 kilograms. Okay. An average force of 480 in a direction opposite the initial 32 meters per second. So my initial velocity here is 32 meters per second. This force is acting opposite. So the ball comes in, gets hit by a bat, goes out. I'm looking for my V final, which I'm assuming we're probably trying to find here, and I know this is going to be negative. And my force is acting opposite of that motion. Also, the way it describes that, my force is going to be negative 480 newtons. And we have a time interval of 0.017 seconds. The final velocity, yes, I'm right. That's what we're trying to calculate. So I'm just going to write down my equation to get used to it. I know that my force times my change in time is equal to my change in momentum. And I know my momentum is mass times velocity. So force change in time is equal to mass times V final minus mass times V initial. This is my change in momentum. And let's see, I'm looking for V final and V initial. We've got that. So let's solve this for V final. So if we solve this for V final, I'm going to bring my minus mass V initial to the other side and make it positive. And I'm going to divide everything by mass. Now, another student asked me a lot, why don't the masses cancel out? Well, if I divide these individually by mass, this mass here would cancel out, and we would just put it under here. That would work, right? Or we could just put the whole thing under a mass. So we'll go force, change in time, plus mass, change in velocity. We'll just put the mass down here like this. Again, you could split this up, cross this mass out, and you'd still have a mass over here. Tomato, tomato, I don't know if it matters that much. So if we plug this baby in, we're going to have minus 480 newtons. Acting 4.017 seconds. All over my mass of point. If we plug this in, we should get what? Negative 22. Negative 22.4 meters per second. Okay, good. Now, let's look at this. Yeah, meters per second. So just like we did conservation of energy, we're going to do conservation of momentum. Now here's how this works. Momentum of object 1 initially plus the momentum of object 2 initially should equal the momentum final after there is a collision plus momentum 2 final. So we really do this. This is after. So you could say this is initial, this is initial, this is final, this is final. But this, what's that sign I'm blanking out? What's this? It's like an apostrophe. Is that an apostrophe? Yeah. Was that prime? It's a prime. Yes. This is prime. So they'll call this P1 prime. Okay, so let's look at something like this. So for a completely elastic collision, this is going to be a lot of your multiple choice. If it is an elastic collision, think of pool balls. That's the very first thing you should think of. That do not stick together. And this is it. Both kinetic energy and momentum are conserved. Okay? Think of pool balls. Kinetic energy and momentum are conserved. An inelastic collision do not stick together. Or they do stick together, sorry. Oh my God. They do stick together. They become entangled. Momentum is conserved. But kinetic energy is not. So we do lab tomorrow. We're going to lose about 78% of our energy. And we'll go through that calculation towards the end. And this is railroad cars hooking up.
So in that way, the elastic
Yes.
or inelastic position, is that where we said we're going to lose?
Yeah, we're going to lose a bunch of energy here for sure.
Not any elastic.
Elastic, we should not. We do lose some energy no matter what. We don't have a perfect situation. And most collisions fall between the two. So we are going to do this baby here. Now these cannons, especially if you look Civil War, they're on wheels, poled. horses, all that stuff like that. But when you fire the cannon, the dang thing has to recoil back, right? Shove the thing back in place, load it again, and... Has anybody been to Gettysburg? If you get a chance, it's very easy to go to Gettysburg, and then from Gettysburg you can drive to New Jersey on the New Jersey side and take a ferry to New York. It's really free parking and everything. But Gettysburg is something that, if you get a chance to go to Gettysburg, you should. You realize the insanity of Pickett's charge and the whole thing back then of people just, anytime somebody got shot in the arm or leg, you just cut it off. There had to be just piles of legs and arms. Okay. Be ready for this. My expert artiste. Here's my cannon. I know you're going to tell me that I should have been an art teacher after this, but... So here's my cannon. Look at my cannon support here. Oh no, what happened? My drawing went awry a little bit. Okay. Let's see what we've got here. So I'm going to label this the mass of my cannon, 1,400 kilograms. The mass of the shell is going to be 60 kilograms. The velocity of my shell is going to be 50 meters per second. Now, what is the recoil velocity of the cannon? Now, in this problem, there's nothing moving ahead of time. These are all after an interaction. So I'm putting my prime there. Nothing is moving before the explosion of the gunpowder. So neither one has initial momentum. So we know, I'm going to write this down, we're going to use conservation momentum. Momentum, I'm going to put initial equals momentum final with my prime. And again, this is always after my interaction. So, if you really wrote this out, if you got used to this, you would say the initial momentum of the cannon plus the momentum of the shell is going to equal to the momentum of the cannon prime plus the momentum of the shell prime. That's everything that's involved in this. Then you could say mass of the cannon, velocity of the cannon, plus mass of the shell, velocity of the shell, should equal the mass of the cannon, velocity of the cannon prime, plus mass of the shell, velocity of the shell prime. But before the explosion, these aren't moving, so we get rid of this entire left side. And we're looking for the velocity of the cannon prime, right? And it should be negative. If we're saying the shell is positive, this cannon should recoil back negative. We'll throw this over to the other side, make it negative. We're going to have minus mass of the shell, velocity of the shell prime, divided by mass of the cannon should be the velocity of the cannon prime. if we plug this in, mass of the shell, we're going to end up with negative 60 kilograms. Velocity of the shell was 50 meters per second, divided by my cannon, which is 1,400 kilograms. If we plug this in, we get negative 2.14, don't we? All right, so that's kind of simple. Next one. We're going to need all the room we've got. Here's what we've got for this situation. And I'm going to do this like, set it up like the air track. Calculate the velocity of two objects following an elastic collision given that M1 is going 4 meters per second. V2's at rest. Now, these masses, this is 0.5 kilograms, 3.5 kilograms. This is what it's looking like. What might happen here after they collide? M1 could bounce backwards, correct? Probably bounce backwards, because then this is a big pig here, huh? This is 7 times more mass. This is going to have some velocity. Now let's use some common sense. If they had the same mass, what's V2 final going to be if they had the same mass? 4 meters per second. And what would V1 final be? 0. Okay? But they don't have the same mass. So if you're looking at a multiple choice test or something like that, for sure you can probably cross out, you know, if they say what's V2 prime or final, it's probably not going to be 4 or higher, right? Okay, so let's set this up just like we did before. So I'm just going to bring this diagram up here, and let's see what we're looking for. Calculate the velocity of two. Okay, we're looking for V1 prime. So for this, we're looking for V1 prime, and we're looking for V2 prime. And I'll use some different colors here. So we know that the momentum initial is going to be equal to momentum final, prime. So I got to keep track of everything. So I'm going to go M1 V1 initial plus M2 V2 initial should equal to M1 V1 prime plus M2 V2 prime, right? And we are trying to find V2 prime. And we're trying to find V1 prime. But at this point, we have two unknowns here. So we know that momentum is conserved. What type of collision is this? This is an elastic collision, so what else do we know? Kinetic energy is conserved, right? So we are going to start out with momentum. We're going to have conservation of momentum and kinetic energy. Solve for one, plug it into the other. So if we, first of all, what's zero for this? All right, so this baby here is 0. If we solve this for V2 prime, we are going to end up with M1 V1 initial minus M1 V1 prime that's V2 prime, right? Nothing overpowering there. So that's conservation of momentum. That's what we know so far. And we could factor out an M1 if we wanted to. I don't think it's going to do us any good at this point. So now, let's go with kinetic energy. So we would go 1/2 M1 V1 squared initial. Look at all this, huh? Right? 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared equals 1/2 M1 V1 prime squared.
Come on, dude.
Oh, we're using finals for these. I'm sorry. We're not using primes. We're using finals. The same thing. Plus 1/2 M2 V2 final squared. And what do we know is 0 for this? We know that this right here is 0. What else can we do to clean this one up? We multiply through by 2 or divide by 1/2, we get rid of all those, right? Does the same thing. We got a 1/2 in every expression. So now, with kinetic energy, they use the finals, but it's the same. These primes in the finals, when we put them together, it's going to be the same thing. So I'm just going to rewrite this. So right now we have M1 V1 initial squared equals M1 V final squared, which is the same as my prime, plus M2 V2 final squared. Well, I know what V2 final should be using conservation of momentum. My prime We got to put that in right there, right? That is what V2 final is. All right. Let's see if we can figure this out. Oh!
Which one is V2 final?
Well, let's say that again. We need to find V2 final and V1 final. Both. Now, so now we have this. We have M1 V1 initial squared equals M1 V. This has got to be a 1. I'm missing my little 1 here. M1 V1 final squared plus M2 here. Now here comes the rest of this in, and it's going to have to be squared. Now, let's see if we can, let's square this top expression. If we square this top expression and factored out, we got to factor out an M1. Let's look at that. Let's take a side note. Watch this. If I factor an M1 out, and then I have V1 initial minus V1 prime, right? And I still have my M2 down below. I'm going to put my M2 over here. That's my exact same thing as this, isn't it? Now, I have to square that, right? Well, it's easy to square these two, because you can just put a square and a square. What about squaring this? We got to use a FOIL, huh? First, outside, inside, last. That's still the way they talk about it? First, outside, inside, last? The F word in high school? Well, we can do that because this is going to be M1 squared over M2 squared times, this is going to be done by, oops, let's put this whole thing up here. This isn't so bad because this is going to be V1 initial squared, right? You line this up by itself. This is going to be V1 initial squared minus, what are we going to get? We're going to go minus 2 V1 initial V1 prime plus V1 prime squared. Isn't that what it would look like if we just squared that? We're doing this, right? Times itself. Right? This is what we just did. We squared this. This is my first. That's my V1 initial squared, correct? Now, if I go out, then this is my outside, right? This is my inside. That's where my 2 V1 initial V1 primes comes from. 2 of those. And then minus, and this is my last. So that does work. Now, that's what we got to add to this, and it's going to look like this. So my M2 still stays here. And now I'm going to have m1 squared. I'm going to put this in red.
Are we multiplying with all that, or are we adding it to it?
We're going to put this whole squared term in here, so I'm going to put it in red. So this is going to be this term squared. So the 1's going to be factored out and squared.
I did not leave room for that.
The m2 over here is going to be squared. And then we're going to end up with v1 initial squared minus 2v1 initial v1 prime plus v1 prime squared. I didn't leave enough room either, Bob.
Then let's not do it.
Oh. Now, let's see if we can fix this thing up. Let's see if we can, we're going to put some numbers in here and see if we can fix this up. Let's try to reduce this down some. Now, first of all, let's do this. This m2 here and one of these m2 squares cancels out. Well, let's put some numbers in here and clean this up. So this one cancels out. I'm going to cross off the square. Now, we're going to put some numbers in here. Let's get some numbers to reduce this down. So this right here is 0.5. That is initially going 4. So we got to square it yet. This right here, mass 1 is 0.5. This is V1 final squared, which is V1 prime. So I'm gonna leave it like this. Now, what else? How about M plus M1 over M2? 0.5 over, and that's got to be squared, doesn't it? 0.5 squared over 3.5. Right? And then V1 initial squared. 4 squared, right? Minus 2 times V1 initial, 4. That's what we're looking at yet. It's the same. Okay? Oh no, that would have made it look too easy. This is V1 prime. This is V1 prime yet, right? And this is still squared. All right. This is all going to clean up. Here's what we're going to have. We're going to have 0.5 times 16, correct? So 0.5 times 16, we're going to end up with 8 equals 0.5 V1 prime squared, right there. Plus, we distribute this through. This is going to be 1.1424 minus 0.5712 V1 prime plus 0.0714 V1 prime squared.
So 0.57,
12, yes. Yes. Because now we're going to clean all this up and use the quadratic. We're going to set this equal to 0 now. 4-hour exam. If we combine all this, this is 8. This 8's going to come over and be negative, right? Okay, but let's put my V1 squared first, so it's going to look like this. This is going to be 0.5714 V1 prime squared. There's my x squared term. Right? All I did was add my 0.5 and my 0.0714. Then, here's my V1 prime. So this is minus 0.5712 V1 prime. And then my 8's going to come to the other side and be negative. I'm going to have negative 6.857. Grab your calculators and solve this when A is equal to 0.5714. Yes. This one right here? It came from the 0.5 V1 prime squared here and the 0.0714 V1 prime squared here. Yep. I should have a highlighter. So B is negative 0.5712, and this C is negative 6.857. All right? All right, let's see if this pig's going to work. Here we go. Program. 0.5714. What? That didn't work. Oh. I don't think my program's working right. Yeah, who's got it? Who's got it? Come on. What do you got? What'd you get? 4 and negative 3? Did you get answers of 4 and negative 3? No. What do you? What'd you get? You should get 4 and negative 3. My program shut down. I don't have my other calculator. Don't we get 4 and negative 3? All right, good. We got it. So here's what we got. V1 prime equals 4 meters per second, and V1 prime equals negative 3 meters per second. Those are my roots, 4 and negative 3. Which one of those is not possible? There's 2 roots, right? Which one of those is not possible? Well, the negative 3 would throw it back. This 4 is not possible. Because this started at 4. It hit something that's 3.5. It can't continue at 4. So this one here is not possible. So this, it goes backwards, right? It goes backwards at 3. Now, if we go back up to the beginning, let me draw my arrow. We just about got this pig. We just about got this pig. Yes.
So get a stretch piece of paper
Well, maybe there'll be a shortcut. Maybe.
See, I knew
I've already seen the shortcut. I've passed this.
Now, if we plug this in for V2, put your arrow down for M1. V1 initial was 4. And minus M1, 0.5. And V1 prime is negative 3. We just solved it. All over M2, which is 3.5. That gives us V2 prime. You get what? Uh-oh. I got 1. Do we get 1? So V2 prime is equal to 1 meter per second. Real applied math. This is refrigerator art. You're going to laminate this and just leave it on your refrigerator for life.
Sorry, that was a final suggestion.
Okay, let's
Go home.
let's talk about lab, which is going to be our last slide. Go to the slide that looks like this.
Ron, we need to talk after class.
Go to this slide.
I've already done these summary.
Let's talk about this. This is our lab tomorrow. We are going to fire this into our ballistic pendulum. It's going to go up and it's going to tell us this angle. Right? Now, this is what we previously did. We did this problem using conservation of energy. Up here at the top, we know that our potential energy here is the mass of the ball plus the mass of the catcher, GH. We did that problem. This is the ball plus the catcher. This is a previous homework problem we did. The kinetic energy up here is equal to 0. We know using conservation of energy that the potential energy down there is 0. Our kinetic energy that heads up at is 1/2 mass of the ball, mass of the catcher, velocity squared. And we called that the ball catcher velocity. Now, for your lab, we're going to lose about 78% of this energy. But because this is an inelastic collision right here, kinetic energy is not conserved. We're going to lose 78% of it. But momentum is. So if momentum is conserved, we're going to calculate this initial velocity that comes out at, the muzzle velocity again. And again, back in the day, I would have walked in here with a 22 strapped on me, and I'd have had a piece of oak here, and I just would have shot the dang thing. Those good days are gone. And we'd have calculated this out by how much the block of oak went up. Now, we are then just going to finish this off with, and by the way, using conservation of energy, using conservation of energy, what did this go up at? The velocity of the ball catcher goes up at the square root of 2gh, right? And when I use conservation of momentum, that's going to be my prime. Now here comes my conservation of momentum. Mass of the bullet, velocity of the bullet, plus the mass of the catcher, velocity of the catcher, 2, mass of the ball, velocity of the ball prime, plus the mass of the catcher, velocity of the catcher prime. Oh, this is perfect timing. But that ball is embedded into the catcher, correct? These primes are exactly the same. So if we factor out this is the ball catcher prime right here. The velocity of the catcher right here initially is 0. No, they're not going to change. So we are looking for the muzzle velocity of this ball tomorrow. We'll use conservation of energy to figure this out. Right? We can solve this side of our momentum equation. We're going to be able to mass the ball. Using conservation of energy, we should be able to figure out the velocity of this ball. We are going on setting number 3, by the way, not 2. We've done all the settings before on 2, and the velocity was about 3.5, right? I don't know what it is on 3. We're going to find out. So we know the velocity of the ball then is going to be that should just come out then. So we'll do a little bit of energy. And if we plug this in with a block of wood here, we get 235 meters per second. But this is our lab. Conservation of energy will give us the velocity down here at the bottom of this baby. And that had to come from the ball hitting it. So I will put that lab online. I got to get to grading those other ones. I'm a little behind on my lab grading. So lab tomorrow, I'll get that out to you.